Hey everyone, Mr. Anderson here, and today we're going to talk section 522 in our CPM ebook, and our notation and terminology are going to grow today. I'm going to throw at you guys some terminology for some specific types of sequences that we've used before, but we haven't necessarily heard the words that describe them completely, and I'm also going to give you guys some very specific mathematical notation that we're going to be using for shorthand, right? Because of course the goal to communicate well is one of the most important goals. Okay, in our notes I've got two different types of sequences described, and there is a sequence over here in purple, and it's describing something called an arithmetic sequence. And an arithmetic sequence is usually very recognizable for us as mathematicians. It's a sequence of numbers where the difference is constant between consecutive terms. How to put it? We're adding the same thing every single time, or subtracting, right? We're going up by the same number, or going down by the same number. So am I adding 3 every single time? Am I subtracting 5 every single time? What's happening, right? Adding and subtracting create a common difference. The other kind of sequence that we're going to be talking about, or we have talked about already, is the geometric sequence. And that's a sequence where the numbers are in common ratio, right? So in order to go from one number to the next number, I'm multiplying by the same thing every single time, or I'm dividing by the same thing every time. And again, we saw a lot of that in our some of our previous work leading up to section 5.2. So yeah, the bunny problem, for example, there was a common ratio between the terms in the sequence, okay? And we've got a sequence here that's really going to help us kind of nail down some of this stuff, as well as some of the mathematical shorthand, so to speak. And the sequence is right here, and it is -9, -5, -1, 3, and 7. And we're going to talk through and walk through some of these things. The first thing they ask me, though, is it arithmetic or geometric? Well, I've got to go ahead and circle arithmetic here, because I notice that to go from -9 to -5, and -5 to -1, and -1 to 3, and 3 to 7, I'm adding 4 every single time. So what I can say here, I can write that sentence, I'm adding 4 every single time. But because that is a common difference, we use D for common difference, and I can just write D equals 4. I'm going up by 4, right? And if you want, you can note that up here if that's helpful. But remember, it's got to be common, so it's got to be done every single time. Here, my first term of the sequence is -9, and that's awesome. I'm going to need that for some work in a minute. But how do we say that? Again, you could write a sentence. The first term of the sequence is -9. But additionally, we can tell everyone the first term of the sequence is -9 by letting them know T is our identifier for the sequence, T for term, and then in parentheses, what term number we're talking about. So if I set it up like this, T in parentheses is kind of like function notation for us. T in parentheses, 1 equals -9. I'm letting everyone know the first term of my sequence is -9. It's not necessarily related to part B, but if I wanted to tell everyone what the second term of the sequence is, I do that. And then I could say, hey, that's 5. -5, I'm sorry. I could then go on. I could skip a couple. I could say the fifth term is 7, and I could keep going, right? When the sequence generator adds a number to each term, the value that's added is known as the common difference. We kind of talked about that in part A. What is the sequence generator, right? Ladies and gentlemen, it's the same. It's the same thing as we see right here in part A. It is our common difference. We are adding 4 every time. Okay, that is what's helping us generate that sequence. Okay, now in part D, we're going to go ahead and connect this to a table, and I've got the table set up to save a little bit of time, and my table might look a little weird at the onset here, but I promise it'll make sense by the time we're done. And we're going to compare the table, the term number n, to the value of the term t of n. Okay, so as we saw up in the earlier part, in part B, t of n describes the term n is just going to be that term number. So we said the first term was 9, the second term was -5, the fifth term was 7. Okay, I could fill these in as well. All right. And what I did here intentionally to kind of help us with E was I left a blank in there. Okay, and you guys can of course look at the top row of my table and fill in that blank. 1, 2, 3, 4, 5. Well, what needs to come before 1 in order to make this work? Well, okay, yeah, that's probably pretty obvious. But how do we fill in the last cell of my table here? And it's actually not as bad as you might think, because there's a pretty nice pattern going on. You guys can see this, right? We saw this up above. To go from left to right, we're adding 4 every single time. Okay, well, in math, we have these things called inverse operations, and if we do this way, we, do something. In this case, we're adding 4. But then if we go backwards the other way, we have to do the inverse of that. So ask yourself, what's the opposite or inverse of adding 4? And we can work the exact opposite direction, and we can subtract 4 every single time. So notice 7 minus 4 is 3. 3 minus 4 is -1. -1 minus 4 is -5. -5 minus 4 is -9. Now, what is -9 minus 4? And ladies and gents, it works out to be -13. So what I would do here is I would tell everybody that and this sounds weird, my 0th term is -13. Now, the reason we care about that is for something we're about to see here. We're going to connect this table to a graph and an equation. And that 0th term, I think you guys know how that maybe reveals itself on a graph. Okay, check this out. Part F, no surprise, says to graph the sequence, should it be continuous or discrete? Now, I have discrete circled, and we'll talk about that as we get going, but I set this up ahead of time for us, and it's on my Desmos machine. I simply just clicked add, and then I added a table, and I pre-populated all this just to kind of show you I can put in that 0th term, and they don't need to be in order. It sure would be nice if they were, but they're not. But look at that pattern. Look what this sequence forms. I think it's probably pretty clear that we could draw a line between all of those dots. Now, do we or don't we? Because that's the question. Is this continuous or discrete? Well, Anderson, you already circled discrete. Why? Well, ladies and gentlemen, we use natural numbers to describe a sequence. And those natural numbers are counting numbers. Okay? So I could have a first term, a second term, a third term, etc. That's no surprise. But can I have a term in between 1 and 2? Can I have a 1.5 term? And the answer for us, using sequences, is no. No, I can't. Okay? I can only have whole number terms, or 0 terms. I can't have negative terms. We're going to see that in a minute. Which is why we're not going to connect this graph. All right? It's why we are dealing with a discrete graph, or a discrete, unconnected graph, a graph that is not continuous. All right? Back to our notes here. And I've got a couple things here in G that I kind of put down. It says, write the equation beginning with T of n equals for the nth term of this sequence. And I did a couple things here. I went all the way back to what you guys see right here, to like chapter 2, y equals mx plus b form, slope-intercept form, because that's really what I'm about to use here. And I even have function notation just to show you real quick kind of the connection. The slope is the same, the input's the same, the independent variable, right, the input, the y-intercept is the same. Well, it all connects here as well. Okay, this right here, this T of n is, I should use a different color. This right here, my T of n, that's just my output. All right, that's my dependent variable. This right here, that's just my slope. This is my independent variable. In this case, it's n, not x. And this is just going to be my y-intercept. Okay, so it's actually really gosh darn easy to write, and it's super doable here. T of n equals that common difference, 4 times n, whatever term number I care about, plus that y-intercept. Now, I could write plus -13, but in this case, I'm going to write minus 13, because recall, ladies and gents, that's my T of 0. and that's why we worked backwards to find that. Okay, keeping on, right? What is the domain? This is a tougher idea, but it has to do with why you won't see me graph anything to the left of the y-axis here. All of my domain values are going to be non-negative, meaning 0 or positive values. I can't have a negative term number in a sequence. It's not the way we count things, okay? When we count, like when we count physical items, which is what a list creates for us, is we don't count negative items. Okay, so we have to have all non-negative end values here, and that is how to put it. That's a bigger idea to understand. That's one we're going to continue to unpack as we move forward. Okay, how is the common difference related to the graph? The common difference is simply my slope, and I've got that. My writing is a little sloppy, but that common difference, D, is just my slope, so D and M are the same thing. All right, and then I've got here another equation that is really going to, another problem, I'm sorry, that's really going to help us, I think, with this particular idea and understanding. And if you need to pause this video, I'm going to try to cruise a little faster so we can make it. But we've got a sequence here. We've got T of n equals -4, -1, 2, and 5. So what are the first terms and what is the 0th term? What is the common difference? Well, the first term is really gosh darn easy to identify for me. And I can see it there. T of 1 equals -4. The other thing that I really want to identify quickly is that common difference. What am I going up or down by? And this one's pretty nice. I'm adding 3 every single time. Okay, so if this is T of 1, I can work backwards by 3 to find T of 0. Okay, so do that real quick and pause the video if you need. Ask yourself, work backwards by 4, what's T of 1 minus 3? And that answer is -7. Okay, right? Because here I was moving forward by 3 every single time, right? 2 plus 3 is 5. That's probably the easiest spot to see it. Now I got to work backwards from 3, or backwards by 3 from -4. That gives me -7. Okay, then it says write that equation. Well, one more time, I'm going to remind you. T of n equals D times n plus T of 0. Okay? T of n equals that common difference, 3, leave the n in, plus T of 0 minus 7. There you go. There's your equation. All right? I promise you, I did verify this, that this will work. I'm not going to do it for the first 4 with you, but I will do one of them with you. Let's just calculate T of 3, right? That's going to be 3 times 3 minus 7, T of 3 then, right? And that's just notation. We'll leave that in. 9 minus 7, T of 3 then is 2. Well, check that. Is the third term 2? And I think the answer is absolutely. Okay? Now, check this out. Is it possible for T of n to equal 42? Well, real quick, I'm just going to go ahead and do some quick solving. I'm going to say 42 equals 3n minus 7. If I add 7 to both sides, I get 49 equals 3n. And then I divide by 3, I get 16 and a third is n. Okay? As we discussed, that is a positive number. It's not negative. But is it a whole number? Remember, when we count 1, 2, 3, 4, 5, right? That it needs to be a whole number. Okay? So, answer to this is unfortunately, no, that's not possible. I can't have a 16 and a third term number. Okay, so that doesn't work. Now look at this, because D asks me something slightly different. It says consider the function. Right? I know that looks very, very similar, right? These two things look very, very similar, but what's the difference, right? X can be 16 and a third. You can see my math there. Check it if you need. X can be 16 and a third. The difference is that's going to be continuous. We aren't given the constraint that our answer needs to be a whole number there. Okay? And in part E, you see that description written in Anderson shorthand. Explain the difference between T of n and f of x that makes your answers to parts C and D different. And the answer is x can be a rational number. N cannot. All right, folks, a little bit of review preview. Check that out. give yourself the ideas that maybe you need to ask some questions about and get those questions asked and answered. Ladies and gents, thanks for watching. Have a great day.